that the
May
system...
I have your attention, please? The building is now closed to visitors who are not escorted by a member of the Georgia Tech community.
Hi, I'm Sarah Jane, and we are presenting on our reusable lunar access vehicle.
I'm Ted Kimberling.
I'm Daniel Kilgore.
And I'm Sean, South of Oregon.
Okay, so the overall big picture of this project is to facilitate the transportation of people and resources to and from the surface of the moon. And this project really emphasizes having a short lead time, a low risk and cost, and overall being very modular and reusable for future expeditions. And the importance of this is that if we have this lunar transport vehicle, it will be a unifying component of the architecture for human cislunar operations and lunar surface access. So it's going to be a major component of the Deep Space Gateway. The moon is also an excellent environment for testing systems and serves for a use in extended space exploration. The moon also has lots of resources on them, and one of those resources is helium-3, which is very valuable for us on Earth. So you could potentially mine that resource. And this project will serve as a baseline for solar system expeditions. It can help with Mars long-term planning. Astronauts can come to the moon and learn how to test to be in a space environment. And this gateway will act as a refueling station for future missions. And then here is an overall concept of the different phases of space exploration. So we are currently in phase 0, where we just have the International Space Station. And then this lunar access vehicle will be part of phase 1, which is where we begin cislunar space. And then if this is successful, then we can create more economic opportunities through phase 2 and phase 3, where we begin going to Mars and increase our solar system exploration. So this isn't the first time that we have been to the moon. We have all of these similar concepts up here, the oldest being the Apollo lunar module from the 1960s. And the thing about this is that it wasn't modular. So this lunar lander, this entire new concept is that it's completely reusable. And then new developments have occurred with Lockheed Martin with the Orion spacecraft, but this one doesn't have landing capabilities. And there's also these other 2 lunar landers, but they haven't been as extensively tested, and they're not made to run for 10 years. And then the reason why all of this is possible is because of new opportunities within the space technology field. For one, there's a huge increase of private investment into space exploration, so it's a lot easier to launch vehicles up into space. There's also new technology such as autonomous robots, electric propulsion, and additive manufacturing in space, which allows for increased means of manufacturing. And then another thing is in 2019, NASA has its biggest budget, so space policy is really in favor of space exploration, which allows us to build a lunar surface access vehicle.
Our main stakeholders will involve government space agencies, both international and national, such as NASA, ESA, and will involve a hint of collaboration with the U.S. government, as well as independent contracts with private companies such as Boeing and SpaceX. So the interest that sparked off this project involved a need to have convenient access to lunar-based resources and a way to establish a testing system for extended space explorations to other planets such as Mars and beyond the solar system. And so we've identified different goals in this project. One of the main one is to develop a means of transporting people and products to the surface, to anywhere on the surface, from the Deep Space Gateway and back. And in doing so, we want to emphasize on the idea of reusability and reliability. And that's really our primary concern with this project. And we've also taken into consideration some other secondary factors, such as commercial viability, or the amount that we've made for each unit produced, and as well as the scientific capacity of the vehicle. So here is a general overview of the ConOps, or the concept of operations. And some key takeaways from this involve the use of a powered descent and ascent module over here at the top, where it shows a separation between a transfer module that will be undocked from the Deep Space Gateway, and once it reaches the surface of the moon, it should be able to sustain crew operations for at least 24 hours before it will have to be deployed back to the gateway through the transfer module, which will stay in orbit relative to the lander. And we also involve the communications between the Deep Space Gateway and the lander. So there will be a three-way sort of communication trade that will occur between these three components.
A project of this size will be encountering a variety of different challenges along the way. One of the major ones is the harsh lunar environment that we'll be operating in, and having to interface with the Deep Space Gateway and other third-party systems. It also becomes much harder because we are having to transport people and make sure we keep them safe and alive. In addition to that, we will be having to navigate the political landscape because we are working so closely with NASA with such large budgets to make sure we keep our project alive throughout a long time. So I mentioned the lunar environment. It's a very difficult area for a spacecraft to operate in. For one, it's covered in a thick layer of lunar dust that can get in and wear down components, which, because we want reliability and reusability, we're going to have to really work to negate. There's also an extreme amount of temperature variation between the hot and cold parts of the moon that we have to worry about. We have to operate in darkness, which is also a problem. And we also have to worry about a heavy amount of radiation from the sun, among other things.
So these are the overall requirements for the system as defined by our objectives and needs. And the main components are that the system needs to make its first trip by December 31st, 2028. The cost cannot exceed $10 billion, and it must exhibit capability between crew and cargo loads and be able to be reusable for multiple trips. So these are all of our different subsystems that we've defined with each subsection of avionics, human support, structures, propulsion, power, and communication beneath them. So the subsystem requirements for avionics are centered around its landing capabilities because it is an intense lunar environment and it's interfacing with the Deep Space Network as it has to have enough control capabilities to dock with the Deep Space Gateway.
All right. So for the recruitment, the requirements for the life support, the vehicle must support 4 crew members from the Deep Space Gateway to the lunar surface, allow them to survive in the vehicle for 24 hours, and then back to the Deep Space Gateway. As well as that, it must have enough appropriate equipment to carry out their duties on the lunar surface, wherever that may be. As for the structure, it must have a capacity of at least 15,000 kilograms to the surface, and then since it's going to require a lot of fuel to get back to the Deep Space Gateway, we're going to reduce that from about to 10,000 kilograms. As Daniel mentioned, the lunar surface is very abrasive and wears down components, so it's got to be durable enough to withstand all that, and as well as all the components that will be mentioned later. It's going to contain an airlock system so that we can get cargo, crew members, and what other equipment out to and from the vehicle.
So the propulsion for the vehicle is obviously critical. So our propulsion system must be able to take the vehicle from the Deep Space Gateway, land it on the surface, and then take it all the way back to the Deep Space Gateway, all without refueling and without excessive strain on the astronauts or cargo. So our vehicle will also require electrical power throughout the duration of the flight of at least 2.5 kilowatts, and we will need to be able to provide this throughout lunar night while on the surface, and we also are going to have to be able to discharge in the excess heat that's generated by this power system.
So the requirements for communication emphasize fast communication and low error rates, high reliability, and low power consumption. The communication also has to work between both the lander and the Deep Space Gateway, as well as the lander and the Earth.
Based on the requirements we've established in the previous slides, we've compiled a morphological matrix that lists all of the possible alternatives that we could implement for each of our subsystems. For the rest of this presentation, we'll be focusing on 2 of the subsystems, power and communications, and conducting trade studies to analyze which of the alternatives would be the best choice to implement in those subsystems. The motivation behind using a trade study for power is because the type of power source that we implement in our design will influence how the rest of the subsystems are designed. For example, how the igniter burns when we in the propulsion system, or the types of thermal control systems that we implement. And we really wanted to hammer home the idea of reusability with the power supply. So that's where all this comes in. So the trade study will involve evaluation criteria such as power output, efficiency, life expectancy, cost, and safety hazard. And here is the trade study that we've conducted using the TOPSIS methodology. We've used 4 alternatives listed in the morph matrix: solar cells, hydrogen fuel cells, a nuclear fission reactor, and secondary batteries. And we've conducted an extensive literature review to acquire all the numbers that we have listed in this table. Note that we wanted to place extra emphasis on life expectancy and safety hazard as indicated by the weights that we've listed, and that was because we really wanted to hammer home the idea of reusability, which is where life expectancy comes from, and we wanted to ensure safety for our crew members. And based on all of this, we've identified a nuclear battery to be the best solution to implement in our vehicle.
So a trade study was conducted for communication because the lunar lander is part of the Deep Space Gateway, so a new communication strategy is required. So we wanted to really look at new and potentially better communications technologies because we wanted to evaluate these with existing and reliable communications frameworks. And in this trade study, we emphasized that we wanted the rover to communicate directly with Earth instead of just the lunar station, which brought up new challenges in mobility and distance. And then here are the different communications options. So I did the Pew evaluation matrix. So I used a parabolic dish as the datum point because that is one of the most common communication options used in deep space. However, this dish is not very good for mobile applications. So while this rover is moving, we're going to need different communication options to use. So in my evaluation matrix, I really emphasized uplink, downlink time, reliability, and flight heritage and power consumption as the main things that I looked at. I ended up choosing the phased array because it had greater reliability compared to the parabolic dish, as if one of the arrays on it goes off, then the other ones still work, so it has more redundancy. It also uses less power consumption than the parabolic disc, which is good for long-term reliability. While it does have less flight heritage and takes up more mass, it is still currently being evaluated, so by the time that this rover launches, there should be less complications about it.
So this is an in-square diagram laying out some of the basic interfaces between the major subsystems of our vehicle. So as you can see, power is obviously interfacing with nearly all of our systems, and you can see many of the links between our major subsystems. So these are the final design decisions that we made. So you can see the methodologies that we picked from our morphological matrix applied to each subsystem.
This is a computer rendering of our overall construction and structure of our lunar access vehicle. Some key features we really wanted to hammer home here was Sarah Jane's use of phased arrays, because we really like the reliability of it in case one component goes out, it's still operable. And then Sean's implementation of a nuclear reactor. We really like the power output and its lifespan because when we're talking about reusability, we really want the long lifespan because as we stated in the requirements, we need it to last for at least 10 years. And then some really unique features that we have is the propulsion module can be interchanged from a crew mode to a cargo mode, which has never been done before, and that the vehicle with the transfer module and everything is all completely recoverable, whereas the Apollo lunar module had to be left on the moon, or part of it had been left on the moon and is there until we pick it up.
So in order to verify all of our requirements, we're going to be doing a lot of extensive testing to make sure that this lunar lander will be able to survive in its environment. That includes microgravity, vibration testing, load tests, thermal vacuum, and just general functional tests of each subsystem. We're also going to be observing the lunar module in its day-in-the-life operation and making sure that the communication between the vehicle and the Earth and the moon station are all possible. We're also going to be having an extreme emphasis on redundancy tests to make sure that if one system fails, that the backup is in place just so we have that 10-year reliability. And an overall challenge with our tests is going to be determining the lifespan of all the components because we really want to ensure that we're able to use this Lunar module for a long time. So in order to make sure that we've made the right system, we're going to validate our system by making sure that it still fits in with the Deep Space Gateway and keep it in check with the development of the Lunar Orbiter, and overall ensure that there's a continued interest and investment in space exploration to make sure that this is possible.
And as you can see in this Gantt chart, this is the life cycle and schedule of development. Our pre-phase and phase A and actual phase A is going to be most of our time in the sense of designing and deciding of operations and requirements and whatnot, and that's probably going to last about 9 months to a year. Whereas phase B is kind of getting everything together, like funds and allocations and resources, and that's only going to last about a couple months to a year. And then the phase C is our selection of final design and the what the baseline of the product is going to be and how our vehicle is going to react in the moon and space. And then, as you can see, phase D really takes up the most time, several years, as it's the assembly and integration of interfaces and subsystems and whatnot. And then phase E, although it looks short on the chart, it's actually going to be until we decide that the vehicle is no longer operable. So we plan on it first starting that phase E by the end of 2028, and that's about our entire life cycle of the whole vehicle. So in summary, our real emphasis on the vehicle is reusability and reliability, and you can see that in the components and subsystems we chose, as well as the combination of existing and new technologies. Whereas using the fission reactor, that was stated earlier, and really the key, first ever to get done, like the fully receivable lunar module, and then really we want to hammer home the importance of the Deep Space Gateway, as it'll be like our home base for our vehicle coming and going from the moon. And, all this is to further the deep exploration of space, whether it's to Mars and beyond. But it's also just the moon, the building infrastructure around the moon as well. This is our works cited. And if you have any questions, please contact us at at ae.georgiatech.edu. Great.
7:30 a.m.
Are we good?
May I have your attention, please? The building is now
It
closed
really wants
to
us to
visitors
leave.
who are